it gives us a lot of methods to study inequality in this network, because it's not only that the average degree is different, it tells us that for people who are very well connected, the difference in degree in the number of people who are very well connected, who are blue and red, gets much, much higher. So as you move towards this top of degree hierarchy, red people are just not gonna be there. They're not gonna exist because of this difference in coefficients. So, and these are the people that we choose when we want to diffuse information. So automatically this kind of inequality gets transported into the models of diffusion of information that base people on how central they are, on people who have very high degree. And that's something we notice in the data set, and we're trying to understand it through this model and to mitigate it through these diverse methods. So with this in mind, I want to show a quick overview of what this difference between algorithms actually looks like. An agnostic way of seeding, of choosing a campaign, is what I mentioned before. You just choose based on degree. These are the nodes ordered by their degree. So you have top nodes, and they're blue or red. And as I mentioned, like let's say blue nodes have actually a higher degree. So red are underrepresented in this degree. And you can only choose a certain number of them. So you have your budget. If you're trying to be more diverse, what would you do to restore some statistical parity in these early adopters is that you would simply add more red nodes from the next red nodes in this degree hierarchy, which means you can choose fewer of the blue nodes. You would have a different threshold for how, like the degree of the blue nodes that you need to choose and of the red nodes. And that is the case if you want to achieve something strictly fair. You have a strict condition. If you have like a percentage of red nodes in the population, you want to achieve that particular percentage in the early adopters set. We can also look at something in between. So we can look at a relaxed version of parity seeding, which is we call diversity seeding, and it's something in between. It's not strictly fair. It's just a more relaxed version of it. So we're interested in how do these three compare? What do they do? Do you lose some people in the outreach? And does the fact that you're trying to be more fair in the early adopters help you somehow overall or not? And the answer to that is, I'm gonna try to be relatively quick on that, but is that first of all, both diversity and seeding and parity seeding do work in terms of making things more fair in the outreach. And it's an intuitive result, because if you have groups that connect more with each other and you choose more of the minority group in the early set, of course, they're gonna give that information to their friends who are gonna probably be also part of that group. And that process will mean that in the outreach, in the total set of people who receive this information, it's more fair. You get more of the community you try to get. The part that's not super intuitive is that both diversity seeding and parity seeding can actually do better than agnostic seeding, can get you more nodes overall in the outreach. And not always, but there's a specific condition when you have a large enough campaign for which we can compute an analytical condition given this model parameters, and we can test it against the data set that we have. So when you have a very small campaign, your budget is small, you can't give this information to many people, you end up with a trade-off. Agnostic seeding actually does best, and that's your best choice. And if you want to be fair, you might lose some people. It's not actually that many people in practice, but there are some. If you have a very large campaign, parity seeding will do best. And if you have something in between, then diversity seeding will do actually the best, which is often the case because we don't have large budgets to give this information freely to everyone so easily. So coming back to these three algorithms, I want to show you a quick representation of how they perform to give a sense of how this actually works. In this graph, we're simulating networks. It's a theoretical analysis for this part. And on the x-axis, you get types of networks, the minority fraction. This is a network that looks like a real network that we work with. So it has 53,000 nodes, 2 communities, some homophily. And on the x-axis, 0.10 means that minority, as in red community, is 10%. The rest are 90%. And as you move towards the right, you get to more equal networks. 0.45, you get 45% minority. Yeah. On the y-axis is the size of your campaign, your seed set size. So depending on what budget you have, you can choose different numbers here. And now the regions are colored by when exactly an algorithm performs better than the agnostic one. So in the orange region, when you have a small campaign, agnostic algorithm performs the best. It means that it gets you the most nodes in the outreach. But at some point, we move into the blue region. It's a phase transition where diversity seeding actually performs better. And the more equal the network is, the fewer nodes you need in the seed set in order for diversity seeding to perform better. It's easier for more equal networks to be both fair and efficient at the same time, which makes sense. However, as you move, at some point when you have a really large campaign, and the seed set size increases, basically, we move into the purple region, for which at some point parity seeding does better than agnostic. It always does worse than diversity because it's a more strict condition than diversity seeding. But we don't see the exact same monotonic trend here in this phase transition. When you have very equal networks, it's actually really difficult to be strictly fair because the community of the minority group you are trying to target has already been activated. There's a lot of people there who have heard this information. So it's really difficult to be strictly fair. It's much easier to be fair in a more relaxed way. So with that in mind, that shows that having this relaxed version is actually working well, and you don't need to have a trade-off depending on how your network look like and how big your budget is. In the data set that we work with this data set of from the BLP, which is a network of computer scientists, and we have a graph when somebody cites someone else. And we have two groups here that we're looking at. We're looking at men and women. Women are a minority group. They're about 18%, so about here. And I want to show you a few how a few data points relate to this theoretical analysis. So if we simulate 1,000 seeds, your campaign is just 1,000 nodes. What we see is that the total outreach is best for agnostic seeding, and parity and diversity seeding gets you fewer people, which is what theory tells us as well. At some point, when we get a lot more seeds, diversity should do better. But in practice, it's actually a more hopeful result than what we see in theory. When we simulate this for 5,000 nodes on the real data set, that's when diversity seeding starts to perform better. You get more nodes in this first row in diversity seeding than in agnostic seeding. Not yet for parity. Parity still does worse, and not by much, but a little bit worse. And this is a simulation done over many runs. So it's an average of the outreach. When we move ahead to a higher campaign, to a larger campaign of 9,000 seeds, that's when parity seeding in practice also starts performing better than agnostic seeding. And again, that shows that the theory was a little bit conservative, and in practice, we don't even need that many seeds as the theory predicts, which is hopeful for us to think that there are so many cases in which these diversity interventions and the efficiency don't come at a trade-off. Now, I know we're a bit short on time, so I will brush through to say that in another recent project with my advisor and our collaborator, Chris Reeder, it's not always the case that it comes that fairness reinforces efficiency. And in a model with, again, the same homophily in two communities, when we look at recommendation algorithms, we looked at this data set from Instagram, also with groups of men and women, and we actually found out that the group that had lower degrees actually ended up having even lower degrees after having recommendations. So it kind of amplified this inequality that we saw in the network. And to give you a quick graph on that, if we're looking at the degree that, so on this graph, we're looking at original graph and how the graph would look like for two recommendation algorithms, Adamic Adar in green and random walk in red. And on the x-axis are people's degrees. from 1 to the max, and on the Y, the percentage of women among those with a certain degree. And this dashed line is the percentage of women in the network. So it's about 54%. And women are majority, but they actually have lower degree in this data set, which doesn't say anything about Instagram. It's just the data set itself. So as we move towards high degrees, that's where you get to see this effect of the power law, the two coefficients of the power law being different, because the percentage of women just drops to 0. And what you see in recommendation, when we add these recommendations and look at the graph again, is that the percentage of women drops to 0 much, much quicker. And we're able to show this, that this difference between the two communities actually increases with this kind of friends of friends recommendations. And I think that's all I want to talk about today in terms of this research project, is to think about how we can take into awareness the community affiliation and the network structure that can help us think about these algorithms and how to mitigate some of the issues we get with them. The last part I'll quickly mention is that there's a group that I've been part of and co-organizing, and I wanted to share it because I think there might be a lot of people who are interested in this. It's an online group that meets basically online a few times every couple of weeks. And it was co-founded by a couple of my colleagues, Rendiet Abebe and Kira Goldner. And now it's a few of us who are co-organizing. And what's interesting about this group is that we have different topics that we work on. There are about like 9 topics that people are interested in, and you can be a part of this group and basically meet every 2 weeks to talk to people about your work, do projects together. We worked on a project related to definitions of fairness in machine learning and mechanism design very recently in one of the groups that we're presenting in a few weeks. And these are groups that are very open to people from grad school, as well as from from academia in general, faculty and industry. And we're trying to work with practitioners for exactly these applications to social good that come from different topics, machine learning, mechanism design, and other fields as well. We work with people from econ or operations research. So it's something that we're very much open to collaboration, and it's a great space to collaborate on this topic. So I just want to mention it, and if there's any question about it, I'll be happy to take them and to discuss more about this. But yeah, thank you so much. I think I'll stop here.
Thank you so much. Questions?
I have a question. I thought that was a very nice talk, and you did a good job motivating why we care about outreach in particular. But I did want to examine that assumption because I feel like in a lot of cases, I wonder if the larger problem isn't that the system does not know how to treat information and make recommendations based on things that would interest minority groups, and thus might just recommend them to people who wouldn't be interested in or otherwise move information around in a graph that is less efficient. So if you think of the goal of a social network or any network is to enable communication, targeted efficient communication where you want it to go, rather than just mass transport of information through the network to everyone, I wonder if it doesn't make more sense to try to analyze not just how much information is getting out and where it's going, but also what information that people are actually interested in is getting to its destination from who. Does that make sense?
Yeah, no, that makes a lot of sense, definitely. I think that's a very related question to this, of how, even when you give recommendation, like how do you know these notions of efficiency of recommendation is very different. Like, is a recommendation good because people took it, or is like, how do you exactly evaluate that? And it's difficult to do without or I guess just from like our position in academia, to like run these large scale experiments and see when exactly do people take recommendation, what kind of content do they want to see. And that is related to something I wanted to differentiate between like a small targeted campaign that for that, of course, outreach is not the best thing. The best thing is to like make sure that you target in a good way, that the people who are interested in something, they hear it. The people who are not interested in something, they don't hear it. And for that, you don't really need these like large scale campaigns. You need like small targeted understanding for which there's other methods to make sure that this is the case. The application that like I was mostly focusing on is the one in which you do need large scale information diffusion. So if you're for issues like, you know, in public health, or in if you want to give a certain product that you think everyone should hear about, if you're giving information or even delivering, if you think about information, not only the idea of it, but if you're trying to deliver like stimulus check, how would you do it? You need some sense of like the community, how exactly does the community operate with money? Are you going to do it through checks, through mobile money? Are you going to do it through direct deposit? All of that depends on like how different communities would operate in that way. So one thing I was watching this talk that was interesting, that was arguing that mobile money is the way to go for impoverished communities if you want to target like stimulus check. Like if I get a stimulus check, I'll get it through direct deposit or a check or something, and it doesn't matter. But for more impoverished community, though, like most of the methods just don't work. And I think there's like this conceptual analogy of thinking about the community affiliation when you have this universal message or a government service or a government related information that you're trying to give to people. And in that way, you don't really want to like target, but like that's where exclusion really matters. Whereas in the more like targeted product related recommendation, exclusion is kind of the way to go, because you don't want to give spam people with information they don't care about.
Thank you. That was very informative.
Thank you.
So I have a question. So have you, so in this problem, you are trying to like see the networks like kind of like equally to make the outreach larger. But, and it's, I understand that it's based on the homophilia of like the overall community. But have you considered the case that, let's say I belong to a minority and I want my message to actually spread through the majority? So because, for example, they belong to legislators, they have more power. And if my message reaches there, it's more beneficial for me. So maybe the measure of centrality that you want to use is like, you want to see if there are like some, well, maybe most of the people in this community have good connections with the people of their own community, but there are some exceptions who are well connected to the majority. So have you thought of like redefining your centrality measures or something like that to modify these algorithms for this purpose?
Yeah, that's a really good question too. I think we were working with different kind of data sets that range from people being super homophilic to people being more heterophilic, so having a minority group that actually connects more with the majority. And in those cases, you want to think a little bit differently about it, because of course, if a majority group, or yeah, let's say if a majority group actually connects to like more with a minority one, you don't really need to see the minority because they already get this information from the majority. So you need to think about this like one step of exactly who connects to whom. And I think those model, we were like toying around with model parameters for different kinds of homophily for the groups, because it's often is heterogeneous. One thing we saw with a lot of the data is that minority groups, especially like demographic ones, do tend to connect more with each other. And there is some research that points to like, especially like affiliation groups that tend to be actually way more homophilic than majority groups. And given that in mind, if you're trying to target them, it's easier to do it through like making sure each community is represented. But again, as you said, if the purpose is different, if the purpose is to actually get to particular groups that are like powerful in a way to make a change, then you want to target towards that. And that is, of course, a different process. But yeah, that exact measurement of homophily and how it differs between community, I would be really interested in an experimental study in that. That's more comprehensive. So far, we see just some networks and we kind of measure it, but we don't really know much more than that about it. Yeah.
Any other last questions? All right. Well, thank you so much, Anna. That was wonderful. We'll move on to our next speaker. So our next speaker is Francesco Fabbri. He's a third-year PhD student at Pompeu Fabra University in Barcelona in the Web Science and Social Computing group. His work focuses on analyzing and mitigating unintended and potentially harmful effects embedded in online social platforms, such as social networks, music streaming platforms, or rental marketplaces. He obtained a master's degree in data science and a bachelor's degree in statistics from Sapienza University in Rome.
Okay, thank you for the introduction. You should be able to see my screen now. Okay, great. So I will first thank you to organizers for such a nice event and organizing this kind of event and for inviting me. And actually, it's such a nice coincidence to be after Anna, because it's like you will see a lot of concept that Anna's trying to illustrate before was from a different perspective. So it's like will be super nice, and I will try to enforce some issues and problems that we find when we do research in social networks and inequality. So this line of work is mainly based on studying visibility of people on social networks due to visibility stimulated by content recommender systems. And it's a joint work with my two advisors, Francesco Bonchi, Carlos Castillo, and other folks from EverCAD, which actually is the research center when it provides me the scholarship. I'm a PhD student in Barcelona and Pompeu Fabra University, as already mentioned. So let me introduce you. So the first, the talk will be divided in two parts. Like the first part, I will try to give you the first problem. The second one will be an extension of the first one. So it's really similar to what we saw before. So basically, we are analyzing, it's an empirical study of analyzing how the visibility of users is spread after generating recommendation with a people recommender system. So in particular, we are focusing on analyzing how the homophily inside the social network is affecting the performance of the distribution of the recommendations generated by the algorithm. The big question is like how the level of homophily is affecting the final output and which is benefiting from it, who is benefiting from it. So just to give you a toy example for understanding the study. So like these are two toy example, like two networks which have same distribution of blue and red nodes. When the red is the minority, and then the only difference is the distribution of the edges, in particular for the minority. So we generate the links through a preferential attachment recommender in this case, and then we generate like possible new recommendations. So we look at the structure of the graph, we generate new recommendations, and what is really changing here, because of the distribution of the edges in the minority, is the visibility of the two groups. So the second group is getting like the minority, which before was the one was getting less visibility, which was, let's say, proportional to the size. Now it's getting the most of the visibility from the recommender. And just because like they appear to be more homophilic rather than the other group. So the minority looks to tend to connect much more often with their peers rather to the other group. So this line of work, as I already said, is really strongly connected to Anna work. Indeed, it's like one of the few work justifying our study, which was showing indeed the algorithmic glass ceiling effect, the systematic mistreatment by the social recommender system. On the other side, there are some other studies which were like in the past, which was showing, like for example, the first one mentioned here was showing that comparing before and after the introduction of a recommender inside the social network, you experience some side effects you were not expecting. And on the other side, even the graph itself, when you look at the graph without even using a recommender system, if homophilic, creates disparities in rankings. And still, the rich get richer effect here can be reframed as a few get richer effect. So like only few people gets most of the visibility or the outcome. So the data, okay, you were like discussing about the difficulties of understanding the utility of the users, of the how important it is to understand who should get the visibility, how. The first problem here is, like, as Anna was saying, is like we don't have data for studying such a problem like this. Like we don't have like why not because we don't have social networks, but it's really not common to find demographics or like affiliated to users. And this is why most of the times we have to rely on synthetic data or on semi-synthetic ones. In this case, I'm likely working with data set that have demographics. So in this case, 20 is a popular social was a popular social network in Spain. It was called the Spanish Facebook some years ago. So it's like this huge data set with age and gender distribution. So from this data set, we can access, it was really similar to Facebook. So you can generate networks of who posts on the wall of whom. So in this way, you have direct interactions. And here, as you see, like given the distribution of the demographic you choose, you can basically generate different networks partitioned by age or gender. And Pocket is a popular social network which is freely available on the web, and still it is like as a good social network because it's homophilic too. So this kind of networks gives us like a wide range of configuration when do we have homophilic minorities, natural minorities, and small minorities. And the recommender systems I use to test our hypothesis, so to check how the really homophily is affecting the distribution of the recommenders, are like spanning into the wide range of four range of categories. So we have one is like academic CADAR, which is based on the topology of the graph. The other one is the collaborative filtering approach, which is basically implicit feedback collaborative filtering. The other one is SALSA, which is the random walk approach, which was also the one used in the Twitter study. And the baseline is just like generating random recommendation. All of them select links at distance too. Also this hypothesis is for sticking to real world scenarios, since most of the social networks recommendations tend to recommend you nodes at most at distance, so they don't go farther usually. So which are the ingredients? The ingredients are really basic. So we want to emphasize the role, so how the homophily and the visibility interact. So the homophily is basically the deviation from a random configuration of the distribution of the edges. So we are like understanding how much the community is connected within themselves rather than to the other side. Then what we do, we look at the visibility. So the V that you see here in the matrix, which is basically the number of times nodes of that group is recommended in the graph. So disparate visibility is a measure to compare which group is benefiting more from the recommendations. Intuitively, if it's greater than 0, the minority will be the one benefiting most, or on the other side will be, if negative, will be the majority. So the first observation, just looking at the data that we have, you see, okay, like it's clear that when the minority is homophilic, the algorithms tend to be biased toward recommending them more time. So if you are homophilic, if the community is homophilic, then it will be the one that will be benefiting most from the recommendation output. On the other side, if the recommendation, if the minority side is really small one, and both of them are not such homophilic, then the majority will be the one which will be recommended more. On the other side, this kind of effect is even stronger when you consider, at least for homophilic minority, when you consider only the hubs of your groups. So if you focus on specifically of the top 10% by in degree of the two groups, you will see that the disparate visibility is even larger. And so still the idea of like few get richer is emphasized here. On the other side, looking at the global effect of the recommender inside the two groups, like trying to really decouple how the distribution of recommendations and visibility is with respect to, let's say, like a time 0 scenario, so without the recommendation, we see that within the minority, the rich get richer effect is amplified. And here you can see it from the Lorentz curve that minority is the one which the distribution of the visibility gets worse. And it is not possible to see the straight line, which it would be the in degree, which is basically over, which are like blue and the red are overlapping in the first case. So, but basically in both cases, when you introduce the recommender, you get a high disparity. You increase the disparity between in degrees of the nodes because you increase the disparity in the visibility. I will not focus that much on the synthetic graphs, but on the other side, in order to strengthen our hypothesis, we also look at that synthetic graphs, and which basically confirms our idea. So like that the homophily gets you this disparate visibility distribution. And so basically the homophilic class is the one that benefits the most from the recommender. And also we investigated more deeply which of the two components between relative size and homophily was the one affecting more the final outcome. And we found out that the size, of course, doesn't impact visibility as much as the homophily does. So this was a work presented last year at IWSM, and here I'll leave you the links and information if you want to know more. But like what I want to emphasize is like that this is the first step, and like this is a static scenario. So when you just look at the graph and you say, okay, I just look at what's going on at t equal to 1. So like after one shot of recommendation, the next level is then looking at what's going on when you generate multiple rounds of recommendations. So here what we do, we simulate starting from real data, we simulate new recommendation to inject in the social network, assuming some user feedback. So assuming that the user accept or reject the recommendation, and then recreating new recommendation with new data. So it's in this kind of a loop, we are generating multiple rounds of recommendation in order to evaluate how the recommender in the long term affect the final distribution of the nodes inside the graph, and how the visibility changes along the time. And still, this kind of work, this like focusing on simulation, is super new. It's doing simulation in social network, doing simulation investigating recommender system is kind of a new line of work. Recently, there was this paper last year in FACT conference showing how applying fairness policy can stimulate side effects of machine learning pipelines. Was not a recommendation, was more on classical classification algorithm. On the other side, there are other studies which tend through the simulation to see how user preferences and recommendations interact in order to understanding which will be the potential side effect in the long term. Still, most of these studies are based on simulation, as this one as well, as emphasizing the fact that most interesting thing to do in this case will be playing with real data, right? Trying to understand which is real interaction you can get from the user, but it's kind of problematic. I mean, will be super interesting to see, but it's difficult for us from the academia. So for introducing these multiple rounds of recommendation, we say, okay, we need to simulate the user interaction in the graph, user that interacts with the new links. So we assume really mild assumption on the user interaction, and we try 3 different policies. The first one is basically a lazy policy. We accept directly the first recommendation in the top K. The second one is like accepting uniformly at random one recommendation from the top K. And the third one is selecting the recommendation based on the position in the top K. So like we use the scores generated by recommenders, and then we look at like the position of the probability generated is proportional to the position, to the discount of the position. In this moment, in this kind of experiments, we are not assuming natural growth, and basically we are not eliminating or removing edges along the path, adding or removing edges in the graph. We are just adding edges from the recommender system. We are not removing nodes or pre-existing edges. So first point here is the situation gets worse and worse. Like there is a positive trend for the visibility of the minority. So what I'm showing here is the new visibility getting at each round of recommendation by the minority. On the x-axis, you have the percentage of edges that we added so far from the graph, from the initial graph. And this is basically showing you that the first, let's say, the more sophisticated recommendation algorithms are going at different pace and increasing with along time the effect stimulated by the disparate visibility, because here I'm showing the visibility of the minority, but on the other side, the disparate visibility is becoming more is becoming more and more larger, benefiting because you are benefiting you are benefiting much more along the time the minority which is homophilic. On the other side, when the minority is not homophilic, I will say that like there are some differences among recommenders, but the situation tends to stabilize quite fast. And so this is a first evidence of like align with the fact that as long as you don't mitigate this effect, generating multiple rounds with the same recommenders and like you basically increasing the disparate visibility between the two communities. That before was with that plot where plots were basically with just one policy. So the second assumption will be, but which is the difference between policies? There are not such a huge difference because the results look consistent along the different policies. So here you see that each line represents a different policy, and in this graph is the same homophilic one of before, but the changes are not so big. So you see that there is a positive trend, but the first two algorithms are going faster than the other two. So let's say that the random and Adami Kadar are sort of a baseline compared to the other two, and they go much. The ILS and Salsa goes much faster. Still, the policies probably need to be investigated more to understand how how robust they are, because we are not including natural growth, and maybe we should add some fine-grained user behavior in terms of how utility function define the user preferences. The rich get richer effect here is getting probably is the one of the stronger results that we have, is that basically all the recommender systems, sorry, the two recommender systems ALS and Salsa are enforcing or like speeding up the rich get richer effect in both cases, in homophilic and non-homophilic graphs. And this means that even if you don't consider minority and majority in your distribution, still you will get, let's say, worse performance in terms of increasing inequality among the nodes. Here we are basically measuring the in-degree the distribution of the in-degree through the Gini coefficient. So as you can see, increasing the number of edges inside your graph, you are stimulating inequalities among nodes. And this is getting worse and worse with the first two algorithms. Still, when the minority is homophilic, this phenomenon goes faster. So at the end, trying to wrap up, I hope to stick to the time, and to wrap up the contribution, this is the systematic study of disparate visibility effect produced by contact recommendation algorithms. And here I skipped some on the results on the synthetic data set, but basically real social networks and synthetic data set confirm what we saw now, so that the homophily plays a key role in the visibility. given to different groups, especially when one of the two is homophilic. And most of the times, as I was showing you, and as I was said before in the previous talk, the homophilic group usually is the minority one. Rich get richer phenomena are getting stronger, and when specifically in the minority. But in the long term, this phenomena doesn't really discriminate between homophilic and non-homophilic graph. And this is like something that we prove to happen in both long and short-term scenario. So a long-term scenario show also, let's say, worst, or let's say unpredicted effects. So for the future work, like we hope to raise this key ethical aspect to design social network recommenders. So we hope to design new mitigation strategies. And the last one is like something I want to, this idea I want to stress is like we really need to understand which are the real user utility functions behind this kind of behavior. Because as I was saying, the disparate visibility is for sure a problem. But what we don't really know is like which is the reaction of the user with respect to this effect. I mean, we don't really know if the user will be glad or no to be more or less visible. So what we should really understand is the impact of this disparate visibility over the user preferences. Thank you so much for the time and for, I stick to the time, yes, okay. So.
That's great. So we have a couple minutes for questions. And I'm going to go ahead and take prerogative to start. I'm really interested in your point about how often we don't have this data. You're needing information about the actual users. So, you know, from Twitter, information about who's connected to who is really easy to get, but who are those people behind the accounts is harder to get, either because the sites are actually anonymous and they're designed that way, or because we just can't get access to the data. So I'm curious to hear more thoughts from you on like what you see as a solution to that. Did we lose connection?
I think we lost him.
Oh no. Well, at least we got the whole talk first.
Yeah. I had a question that I guess I don't get to ask it.
Do you want to ask it? It'll go on the recording.
I guess I skip it. Yeah. Oh, he's back.
Sorry.
No worries. That was excellent timing. You made it through your talk. Did you hear my question before you?
I was thinking half of the question, like internet decided I could not, sorry.
So basically, I'm just curious to hear more of your thoughts about kind of data availability and this problem that we so often can't get data about the users behind accounts on social media accounts, which is kind of crucial to this whole question.
It's kind of tricky, right? Because on one side, as a researcher, I will say that I would love to have this kind of data, right? I would love to have the opportunity to interact with those data, this kind of data set. On the other side, I understand how sensitive they are really critic and like super crucial will be not so easy to access this kind of information for many concerns, legal perspectives, and also ethical ones, because, you know, the accessing demographic of the users. Also, if I can imagine, like, for example, the most common one would be Twitter. Even, I guess, from the Twitter side, like from being a researcher inside the company will allow you to access this kind of information because you don't provide to them, no, right? So it will be a semi-synthetic information. Still, so I would say that definitely would be like as a researcher, like I would say I would love to have access to this kind of data. On the other case, I feel the pressure of being, you know, responsible on the individual. So maybe anonymize them and like randomize as much as possible the study as a subset. So I mean, being accountable on the other side, that's someone that studies these effects will be crucial too.
So I have a question about like the long-term thing that you discussed. So I think like these things that you are like homophily or other things that you are trying to measure, intuitively, it really depends on the network you are studying. For example, if you think of Facebook, I assume that these recommendations are like recommendations between people. If you consider Facebook, after some point, you reach some stable point, and maybe actually people start unfriending each other rather than befriending each other. And for example, the BLP, it's not the case. It's always growing. So I wonder if you consider these things when you are studying like these effects in long term.
We were so we were assuming like one basic assumption is like if I like in the multiple rounds, if after one round in the top K you select just ones of them, and the other ones you didn't select will be not shown anymore. So it's a sort of a binary interaction, right? So you decide to choose which one you want to be linked to. The other two will be disappearing for you, so will not again appear again and again, in order to avoid to build this natural network because of the topology. So like even if let's say the most probable one will be not selected by the user, it will disappear in the next round. So yes, on the other side, maybe probably not including the organic growth is the main limitation, because we don't, also it's difficult to simulate. It's like, and as Anna was saying before, you can try to simulate, and sometimes in that case, the algorithm was showing better performances even with the real data, because when you simulate, you're really assuming a lot of interaction, but the network is so complex. So assuming that you don't remove edges is really can be problematic, no real scenarios. So, but yes, we avoid like the first thing. I mean, the first basic thing you can do is just like assuming that you don't want to be reached again by that node. So we drop that recommendation.
Mm-hmm. Thank you.
Any other last questions?
I thought that was really awesome, awesome presentation, and I was wondering what were your thoughts on regarding like this last part you mentioned about how to gauge on people's sense of utility out of the system, how they like, or do we have any like thoughts, like ideas for like any experiments we could do to measure or like elicit their preferences in a way? I don't know if there's any on that, but maybe you had some thoughts.
Yeah, we should. Yeah, maybe probably. Like some basic assumption will be that the ones homophilics, the ones that are homophilic, they want to be, they don't really care about visibility. They just matter of who is the one they get recommended to. So it's like, I guess we'll be defining, it's tricky because usually when you assume user preferences, it's just matter of this global assumption that stands for everyone. But I guess the problem is finding individuals inside the minority that behaves completely different, right? So the outlier you were mentioning before, it will be super difficult to do. A real study maybe will ask us, like, will answer this question, like a real user study. So when you get users interacting with recommendation. Otherwise, it's always not. As soon as you assume, I mean, as soon as you like assume some specific user preference for the group, you say, okay, all the group is like this, but it is not, no, right? Because maybe some of them. Yeah, this is super interesting question. It's like really difficult to. No, but yes, it's like being on the other side will be crucial for me, I guess. No, if you try A/B testing, maybe with data.
Yeah, definitely. Thank you.
You're welcome.
Okay, well, I guess that probably wraps up this first session of the day. So thank you so much to our two presenters, and hopefully we'll see you back at 2 o'clock for the last session of the symposium. So thanks, everybody.
Thank you so much.
Thank you. Bye.
Bye-bye.